So in the last lecture, we have seen that uh, composites of homotopic maps are homotopic. So uh, by using this, we can conclude that there is a category. So, so there is a uh, category uh, pairs, topological pairs, topological pairs and homotopy classes. Means objects of the category are topological pairs and markisms between two topological pairs are homotopy classes of maps between the two topological pairs. So most important part to see this is that if uh, F and G are homotopic classes, right? Uh, of maps would be X A, Y B, Z C. So if F is other conditions will be satisfied easily. If F is a homotopy class of maps uh, between this topological pair to this topological pair, and G is homotopy class of maps uh, between this topological pair to this topological pair, then uh, this uh, is well defined. So how we define this? We'll define this to be class of F compose G. So this will be well defined because this in place of we can have F1 equal to F2, right? And G1 uh, class of G1 equal to class of G2. If this happens, then in order that this composition is well defined, we have to have that F1. So if F1 compose G1 uh, is a homotopic to F2 compose G2. Right. So if this happens, then we can define this. This definition is valid if this holds. But this holds because what is meaning of this? This means that F1 is homotopic to F2 and this means what? G1 is homotopic to G2, right? Because F1 is homotopic to F2, G1 is homotopic to G2, F1 compose G1 is homotopic to F2 compose G2. So we have already seen from the previous is that composition of homotopic maps is homotopic. So by using that, we can conclude that this composition is well defined, and hence other conditions are straightforward. So you can verify that that there is a category uh, of topological pairs and homotopy classes. Uh, Next, uh, uh, so this category uh, we call this category as homotopy category. So we call this, say that category is called as homotopy category. This category is called homotopy category. Now this homotopy category, so it's an observation, the homotopy category of pairs contains the categories of contains as full subcategories. The categories of full subcategories, uh, the categories of uh, the homotopy categories of topological spaces and the topy category of category of pointed topological spaces. Pointed topological spaces. So you can see that you can see that this if we are given a topological space, we can recognize it this by this pair, right? So this is a topological pair, right? We can recognize it this x by this, and this is an object in the homotopy category of pairs, right? So yeah, and this home xy will be actually a home the same as home x phi y phi. So this from this you can see that this homotopy category of topological spaces is a full subcategory. Similarly, homotopy category of pointed topological spaces x x. This is this of course is a pair of topological spaces. You can consider it, and this is an object in the homotopy category of topological pairs. And you can see that this uh, home x x y y. This is basically same in this homotopy category of topological pairs and in the homotopy category of pointed topological spaces. So this homotopy category of pointed topological spaces is a full subcategory of homotopy category of uh, uh, topological pairs. Next, uh, there is a functor. There is the functor from the category there is the covariant functor. There is a covariant functor from the category of pairs and maps uh, to the category of homotopy category homotopy category of uh, pairs whose object function. So when you have a functor, it works. It has two components. One component is an object function. Other component is morphism function. So whose object function is identity TT. And morphism function uh, uh, sends sends a map f to its homotopy class. So what we have is this is uh, category of pairs and homotopy category of the category of pairs. So from this there is a functor from this category to this category. Uh, if we denote that functor by t, then it sends x to given any object here in this category. So we have pairs, right? So given any pair in this category, it sends to that, right? So it is identity of this object function is identity, right? Every object goes to itself. And this morphism function, right, xa to yb, if f is a morphism from here to here, then this sends this to this class, homotopic class of maps of this f from xa to yb. And one can verify easily that t is a functor. Can verify easily that t is a covariant functor. Already we have discussed that algebraic topology is study of some functors, right? From category of topological spaces, from topological category to algebraic category. So uh, um, most of these functors are defined under homotopy category. Now a diagram of topological pairs and maps is said to be homotopy commutative if it can be made a commutative diagram if it can be made a commutative diagram in the homotopy category. So what does it mean if we have right? So if we have a commutative, we have a diagram in the category of pairs, and uh, we can of course put here B, A prime, B prime, one, B. Then this diagram is homotopy commutative if we replace the each morphism here by uh, their homotopy class, right? Then this will be a diagram in the in the homotopy category of pairs, and if this diagram is commutative there, then the original diagram will be called homotopy commutative. Next we have definition. A map f from x a pair to y b is called an equivalence if this is an equivalence in the homotopy category of pairs. So far, because we know that for every map f from here to here, it is going to belong to some equivalence class of right of maps. So if that equivalence class is an equivalence in the homotopy category, then this f is called an equivalence. A map G from YB XA is called, this is called an homotopy equivalence. This is basically a homotopy equivalence if its class is an equivalence in the homotopy category of pairs. A map G from YB to XA is called inverse, homotopy inverse. called homotopy inverse of f if class of G is inverse of class of f in the homotopy category. And two pairs XA and YB are said to have same homotopy type. So pairs are said to have same homotopy type if they are equivalent in the homotopy category. If they are equivalent in the homotopy category. So when do we say that two objects are equivalent in a category? When there is an equivalence between them. Next we have some more definitions. Listen. A topological space X is said to be contractible if identity map Ix of X is homotopic to a constant map of X into itself. In other words, a topological space X is said to be contractible if identity map Ix of X is null homotopic, right? Uh, uh, and the homotopy uh, of Ix to a constant map to a constant map of x to x naught in x is called a contraction of x to x naught. So examples 1 and 2 are actually uh, are examples for contraction. So, so in example 1, we had fxt equal to 1 minus tx for every x in Rn, t in I, right? So here every point here this fx 0 is identity Rn and fx 1 is actually 0. So every point of Rn is getting contracted to 0. Similarly, in the example 2, this 0, 1, every point of this interval is getting contracted to this point 0. So that they are also be defined the homotopy like this. Next we have some results. Lemma. Any two maps of an arbitrary space x to a contractible space y are homotopic. Proof. Let Iy is homotopic since y is contractible Iy is homotopic to C, where C is a constant map, a constant of y to itself. let f naught f1 from x to y be any maps we have f naught equal to I y compose f naught, and this is homotopic to C composed f naught, but this f naught composed C, this is nothing but uh, okay, and this again we have this, and f1 equal to Iy composed f1, and this is homotopic to C f1. Clearly uh, C f naught C f1, hence f naught is homotopic to f1. So one thing so already we have seen that if in fact just this y cross I to y, and then we have x cross I to, so here we can consider uh, f naught cross I identity on I, right? So this will give a homotopy uh, between this and here we have actually the homotopy. Suppose this is f, right? Then we can here f. So this f composed f naught identity and I. This is a homotopy between this and this, and hence because this is this, so this between this and this. Similarly, we can have homotopy by f1 I, because this is continuous, so the composition is continuous. So y cross I to y. So again, f compose this will give you a homotopy between this and this. And because f naught is homotopic to this and this is equal to this, and this is homotopic to f1, and hence f naught is homotopic to f. Next, we have a corollary. If y is contractible, then any two constant maps of y to itself are homotopic also, and the identity map is homotopic topic to any constant. So this is obvious, right? So y is contractible. So any map, right? Any two maps from y to y itself will be homotopic. So in particular, we can take, if we take any two constant maps from y to y, then they will be homotopic. And also, if we take one map as identity map of y and other as any constant map of y to itself, then also they will be uh, homotopic. So we will stop here today.